Box on the Hill, AP. Remember, when we're doing box on the hill, we're going to take our coordinate system and rotate it so the x-axis is in the direction of motion. Gravity is pulling straight down. The normal has to be perpendicular to the surface. He's pushing up the hill, and that means friction is going down the hill. I'm also going to write down the given information, the height, the mass, and the coefficient of friction. Other keywords I see in the paragraph here: constant speed tells me that all the forces are in balance. Our first question wants us to draw the forces. We've already done that. I like to draw the forces separate on the box and on this problem because we're going to have to do components on gravity, and you're not allowed to do components on part A. In the CP class, we call the components Fx and Fy. In the AP class, they usually skip that step and just call it Fg sine theta, Fg cosine theta. Remember, once we find the components, we don't use the gravity ever again, so we just have these 5 forces now acting on our box. Question B is asking us about the normal force that's in the y direction, so we'll ignore the x directions. We know in the y direction those forces are in balance with each other always. The sum of the forces in the y direction adds up to 0. And this is how we write it's Newton's second law, and they do want you to write this out on the AP problems. Rearranging for the normal force, we have Fg cosine theta is m times g times cosine theta. Putting in our numbers, I got 460 rounds to 500 because our 50 only had one significant digit. Part C, they're asking for the component of the gravity that's acting parallel to the plane, so that is the sine side. So Fg sine theta is m times g times the sine. 167 rounds up to 200 again because of that 50 kilograms. Part D, calculate the friction force. Friction is mu times Fn. We got Fn from part B, and remember, it doesn't matter whatever you got for part B, you have to multiply that number times the 0.3. And whether you got this right or not, as long as you're showing your work here, you will get full credit for this one. All right, 138 is going to round to 100 because part B also had one significant digit to it. Part E, calculate the force applied by the person on the box. We're going to have to look at the forces in the x direction, so I'm going to ignore the y forces. We have 3 forces in the x direction. The sum of those forces has to add up to 0 because it says he's pushing at a constant speed. We have 2 forces in the positive direction and 1 in the negative direction. So sum of forces, we do the ones in the positive direction, subtract the one in the negative direction, and they're adding up to 0 in this case because it was a constant speed. Rearranging for Fa, I'm going to add Fa on both sides. Now both of these are things that we've calculated already. The answer to part C was Fg sine theta, and the answer to part D was our friction. So we're just adding those 2 answers together. And remember, if you got either one of those wrong, it doesn't matter. As long as you're showing your work that you're adding those numbers, you get the full credit for the problem. 305 rounds to 300 for this one. The last part, the work done. A inclined plane is a simple machine, and we learned that the work is force out times the distance out. The force out is the weight of the box, and the distance out is the height that it's being lifted. Remember, the F and the D have to be parallel to each other to find the amount of work. The other way to do this is to find the F in times the D in. The force of the input is the person. He's pushing, and he's pushing a certain distance. If this was a simple machine, our efficiency would be 100%, and that means that the work in equals the work out. However, we know it's not 100% efficient because we have friction, and that means these are not equal to each other. Normally it'd be easiest to just multiply these 2 numbers because we already know the weight and we know the height. So we're going to have to use the Fn and the Dn to calculate this one because there's friction. The Fn is the applied force. We figured that out in the previous part. The Dn, we're going to have to use the triangle here. This is a sine formula. The sine of the angle is the opposite over the hypotenuse. And this time, usually we're using the sine formula to find the opposite side. When we're trying to find the hypotenuse, we're going to have to be dividing by the sine of 20 instead of multiplying. So putting my numbers in, the Fa that we got from the previous part was 305, and the Dn is going to be 3 divided by sine 20. 2680 rounds to 3,000 joules for that one.